Section 8.4 is about the properties of logarithmic functions, and we have five objectives, and one of them is to express the logarithm of a product as a sum of logarithms, and conversely, then to express the logarithm of a power as a product, and then the C part to express the logarithm of a quotient as a difference of logarithms, and conversely, then to convert from logarithms and products, quotients and powers to expressions in terms of individual logarithms, and conversely, and last is to simplify expression of the type log base a of a to the k power. So let's begin with the logarithms of products. And so property 1 is the product rule, and it basically says that for any positive numbers m and any logarithm base a, the log base a of m times n is the log base a of m plus the log of base a of n. So in other words, the logarithm of a product is the sum of the logarithms of the factors. So let's do some exercises here. They're very simple, and so they're very easy to understand. Applying the definition to the first exercise. So this would be, for 1, it would be the log base 5 of 25 plus the log base 5 of 5. And for 2, it's the log of base b of p plus the log base b of q. And for number 3, we use the definition in reverse. We start on the right side. We have the sum of the logs, and so that's equal to the product of 7 and 5. So that would be equal to the log base 3 of 35. 7 times 5 is 35. And then for number 4, we add all 3, and so for number 4 it would be the log base a of j times a times m. So you can maybe say that's a log jam, log base a of jam. Little humor here in mathematics. The next rule is the logarithms of power rule, and it says for any positive number m, any real number k, and any logarithm base a, log base a of m to the k power is k times the log base a of m. In other words, the logarithm of a power of m is the exponent times the logarithm of m. And so we have some exercises here. And the first one would be number 5, log base 7 or 4 to the 5th power, applying the rule above here. So that would be the exponent is 5, and that would be the k in this case. So it's 5 times the log base 7 of 4. Now for this one, we can write this as log base a of 5 to the 1/2 power. So in other words, this would be then 1/2 times the log base a of 5. The next rule has to do with quotients, and so the logarithm of quotients says the following. The quotient rule. For any positive numbers m and n in any logarithm base a, the log base a of m divided by n is equal to the log base a of m minus the log base a of n. In other words, the logarithm of a quotient is the logarithm of the numerator minus the logarithm of the denominator. So let's look at exercise number 7. Expressed as a difference of logarithms, applying the rule that we just learned about. So that would be equal to the log base b of p minus the log base b of q. So it's a very simple concept. And here it's the other way. In other words, we start on the right side with a difference of two logs to the same base. So that would be equal to the log of base 2 of 125 divided by 25. And since 125 divided by 25 is 5, this is equal to log base 2 of 5. Next is an exercise that tests our knowledge of the properties of logarithms, and we have to state if that's correct or not. And so the log of 5 times x equals log of 5 times log x. That's incorrect, because it's equal to the log of 5 plus the log of x. But this statement is incorrect. Now the log of 5x equal to the log of 5 plus the log of x. That is correct. And the log of x squared equals to the log of x times the log of x. That is incorrect, because that's equal to 2 times the log of x. So, but this statement is incorrect. The correct statement would be 2 times the log of x. So here is the correct one. Log of x squared is 2 times the log of x, so that is correct. So here with the log of a quotient of x divided by 3, that's not equal to the quotient of the logs. However, it is a difference of the logs. So that's we have in the next statement here. Number 6, the log of x divided by 3 is equal to the log of x minus the log of 3. So that is a correct statement. And the log of x plus 2 is not equal to the log of x plus the log of 2. This would imply the log of 2x. So this is incorrect. And the log of x plus 2 times x plus 2 equals the log of x times the log of 2. That is incorrect also. Because the right-hand side would imply, well, it's not, certainly it's incorrect. Let's leave it at that. So in the next few exercises, we have to express in terms of logarithms of w, x, y, and z. So this would be the same as the log base a of z to the third divided by x times y to the 1/2 power. So it would be 1/2 times the log base a of z to the third divided by xy, and that's equal to 1/2 times the log of z to the third minus the log of xy, and that is equal to 1/2 times 3 log of z base a. Sorry about the base a here. Everything is base a. Minus the log base a of x minus the log base a of y. So that we can write as multiplying by 1/2 would be 3 divided by 2 log base a of z minus 1/2 log base a of x minus 1/2 log base a of y. For exercise number 10, we have log base a of x squared divided by y to the third z. We have the log base a of x squared minus the log base a of y to the third z. And that's the same as applying the power rule here. We have 2 times the log of base a of x minus the log base a of y to the third minus the log base a of z. And so finally we have our answer as 2 log base a of x minus 3 times the log base a of y minus the log base a of z. And it's simply applying all the rules we've learned so far. For number 11, we have a guided solution. The log base a of x to the third y to the fourth divided by z to the fifth w to the ninth power. So first of all, we write that as a difference of 2 logarithms in the numerator and denominator. So log base a of x to the third y to the fourth minus log base a of z to the fifth w to the ninth. Now we're going to write each product as the sum of 2 logarithms. So that gives us log base a of x to the third plus the log base a of y to the fourth minus the log of z to the fifth plus base a of z to the fifth plus log base a of w to the ninth. So that'll be log base a of x to the third plus log base a of y to the fourth minus the log of base a of z to the fifth minus log base a of w to the ninth. And now we apply the power rule. So that then becomes 3 log base a of x plus 4 times the log base a of y minus 5 times the log base a of z minus 9 times the log base A of W. The next two exercises are the reverse of what we just did a moment ago. So we can write the first term as log base A of x to the fifth minus the log base A of y plus the log base A of z to the 1/4 power. So we can combine these two terms here, and so this becomes then the log base A of x to the fifth z to the 1/4 power minus a log base A of y, and we know that this now is the quotient, applying the quotient rule, that's equal to the log base A of x to the fifth z to the 1/4 divided by y. For number 13, we have the difference of two logarithms, so we can write it as the log of base A of the square root of x divided by b divided by square root of bx, or the log base A of 1 divided by b times the square root of x divided by bx. So now under the radical, the x's cancel, and so what we have then is equal to the log base A of 1 divided by b times 1 divided by the square root of b, or b to the 1/2. So that would be the log of base A of 1 divided by b to the 3/2, or we could write that also with a negative exponent as the log base A of b to the minus 3/2. So we can write it in this form or in this form. The third way of writing would be the log base A of 1 divided by b square root of b. So all of these expressions are equivalent. So here you have the solution to exercise number 13. So here we're given the log base A of 2 equals 0.301, the log base A of 5 is 0.699, and find each of the following if possible. So number 14 says the log base A of 4 we can write as the log base A of 2 squared, which would be 2 times the log base A of 2, and so that's equal to 2 times, since the log base A of 2 is 0.301, 2 times 0.301, or 0.602. Similarly, number 15, so this was for 14. For number 15, we have log base A of 10, and we can write that as the log base A of 5 times 2, which is equal to the log base a of 5 plus the log base a of 2. So now we just need to add these two logs, and so 0.301 plus 0.699, and when you add these two numbers you get 1. Number 16, log base a of 2 divided by 5 is log base a of 2 minus the log base a of 5, which is 0.301 minus 0.699, since these numbers are given to us. And so that's equal to minus 0.398. And number 17, log base a of 5 divided by 2 is a log base a of 5 minus a log base a of 2. That would be 0.699 minus 0.301, and so that's equal to 0.398. So the log base a of 1/5 is equal to log base a of 1 minus the log base a of 5, and the log of 1, regardless of any base, is 0, minus the log base a of 5, and that was given to us as 0.699. So that means the answer is minus 0.699. And for number 19, we have the log base a of the square root of a to the third. So the log base a of the square root of a to the third So that's equal to log base a of a to the 3/2, which would be equal to 3/2 times log base a of a. And since the log base a of a is equal to 1, the answer is 3/2. In other words, 7 we can write as 2 plus 5, but there is no formula for the log of the numbers, of the sum of two numbers. So this number 21 we cannot find with the information that's provided here. Next is the logarithm of the base to a power, and that's property number 4. For any base a, log base a of a to the k is equal to k. And that's very easy to prove. let me just do that for you here. Proof: the log base a of a to the k is equal to k times the log of a, log base a of a, and the log base a of a for any base is equal to 1, so it's equal to k times 1, or simply k. So that would be the proof of this property here. It's a great identity to remember, and so we're going to do a few exercises with that information. Here we can use the information. Number 22, log base a of 16 would be log base a of 2 to the 4th power, or 4 times log base a of 2, and we're given the log base a of 2 previously as 0.301, so 4 times 0.0301, which is equal to 1.204. Now, to simplify number 23, so 23, we have log base 2 of 2 to the 6 would be equal to 6 times the log base 2 of 2, and the log of 2 base 2 is equal to 1, so the answer is 6 for number 23. Similarly, for number 24, that's equal to 3.2 using the power rule times the log base 10 of 10, and the log of 10 base 10 is 1, so it's 3.2 times 1, or 3.2. And for number 25, we have, using the power rule, that's 12 times the log base e of e, and the log base e of e is equal to 1, so it's 12 times 1, or equal to 12. And this concludes section 8.4.